actually feel like Aaron probably doesn't need an introduction. Also, I'm really lazy today. So, without further ado, Aaron Patterson.
Yay.
Good morning, everybody. Today I'm going to talk about defragging Ruby. Also, I want to say, sorry, I got the preview slides up here and I'm laughing at my own jokes. I apologize. I just want to say thank you very much for having me here. It's really exciting to be at RubyConf. Ow! So, how was the party last night, everyone? Yeah, I thought it was very enjoyable. It was Tim Tam slamming. Yes! Local jokes. My name is Aaron Patterson. I look different on the internet. This is what I look like on the internet. I invented the Friday hug. Yes, I invented hugs on Fridays. But we're not going to do one. I'm leaving that for a friend to do later today. I'm on the Ruby core team. I'm also on the Rails core team. I'm a Ruby Gems committer, and I work for a company called GitHub. And you may have heard of them. They host Git repositories on the internet, and you can use them. And they kindly pay me to do stuff, which is good. I come from the United States. Specifically, I'm from Seattle. I started up here and then flew all the way down here, so it was very far away. But I wish that the airline company had watched the talk yesterday about the Game Boy, because I think it would have been a lot more efficient if we had just flown straight up and done an overflow. That path might look like it's a little bit longer, but due to map projections, it's actually a shorter distance. This is actually the path that Christopher Colombo took in 1983 when he found Australia. Sorry, I came up with that last night. I was like, that sounds funny. All right, whatever. So before I came to Australia, I decided to learn about Australia's rich culture and heritage by watching all seasons of Summer Heights High. Now, I really enjoyed the show, but I think that Jamae stole her looks from me, and that she's a total bogon. Anyway, my name is Tender Love on the internet. I thought it was very exciting to see Shauna's presentation yesterday with her mom here in the audience. So I want to tell you a little story about when my parents came to see me in the audience. So I'm kind of a black sheep in my family. I'm the first of my family to drop out of college. Which makes me feel really bad. I have two younger sisters. So my parents are both engineers. I have two younger sisters. One of them's a dentist, and the other one's a chemical engineer, and I am the dropout. Anyway, for the longest time, I've been doing programming for a long time, and since my parents are both engineers, it's not weird to them that I make my money by sitting in front of a computer all day. I'm sorry, I'm speaking way too fast for the stenographer here. I'll slow down and try to say something in emojis, because it would be be cool if there was a red heart on there. But anyway, so it's not weird to them that I sit in front of a computer to make my money all day, and I tell them what I do. But there's one thing I've never told them, and I haven't told them that this is my name, or that people know me by this name, and also since I dropped out of school, I'm paranoid that my parents don't actually believe that I make money in a respectable profession. I'm afraid that they think that I'm just somehow, faking it, like selling drugs or something like that, and pretending that I'm a programmer. Anyway, there was a conference in my hometown. I grew up in Salt Lake City. I live in Seattle now. There was a conference in my hometown, And I decided that it would be good for my parents to come see me give a presentation and see what I actually do. So the conference organizer invited me to speak, and I said, yes, I'll happily speak as long as you give me 2 free tickets for my parents. And he's like, absolutely, of course we would do that. So I went to the conference with my parents, I met the organizer, and I said, hey, these are my parents, and the organizer, Mike, he was like, oh, nice to meet you. We've reserved 3 seats for you at the front of the auditorium. I'll take you there now. So he took us down to the front of the auditorium. In the front row, there were 3 seats, and there were 3 signs, 1 on each seat. And the first sign said tender love, the next sign said tender mom, and the next sign said tender dad. And I'm just like, no. Not right now. So I had to very quickly explain to them. I'm like, this is a name that people know me by on the internet. Like, don't worry about it. People might ask you about it, but just be cool. So I made it through, and we've never talked about that since. Anyway, I love cats because I think cats are the best. This is one of my cats. This is SeaTac Airport, Facebook, YouTube is her full name. But we just call her Choo Choo. This is my other cat. He's more famous, Gorbachev Puff Puff Thunderhorse. This is him trying to hide, which I think is hilarious. So SeaTac likes to sit on my desk all day, and she's also a huge fan of boxes, which I think is adorable. Like, just... I also like her a lot because she makes this face, and it's the same face I make when I'm programming. Anyway, I have stickers of my cats, so if you like these cats, I will give you a sticker of them. So I want to share, before we get into the main, important details of this talk, I want to share something with you that I built. First, I'm going to show you a graph of the output of this thing. This is the graph, and I'm going to explain the contraption to you that produced this graph, and you'll understand what this graph is at the end of this. These are the things that I used to build that. I have a bathroom scale, so this is just a bathroom scale which I acquired for free. Through legitimate means. Not stealing people's bathroom scales. This is an MSP430 microcontroller that I'm using to read data off of the scale. Then I have a Raspberry Pi with a motion sensor built into it, and the Raspberry Pi can read the data off of that microcontroller. So I have this contraption mounted like this, where mounted at the top is the motion detector, and down at the bottom of that is the scale. So up there at the top is where the Raspberry Pi with the motion detector is. Down there at the bottom is the scale. And on top of the scale, I've mounted the cat's litter box. And the cat, when the cat goes into the litter box, the motion sensor detects it. And then we start recording data onto the Raspberry Pi, and then when the cat leaves, we stop recording data. So if you look at the graph, this is essentially what that graph is here. So here is where the cat enters the litter box, and that's where the cat leaves the litter box. And the difference between those 2 lines is the amount of weight left over, which is approximately 100 grams. So when I was building this contraption, I was searching the internet for, how to build a cat poop measuring contraption at scale. So I put that into Google, and of course the first result was, have you tried Elixir? And so I think every good project starts with a question. And my questions, I had how heavy is my cat's poop, and when should I clean the litter box? But this isn't my talk, because this previous contraption, this is about garbage collection. And today, I'm not talking about garbage collection today. Today we are talking about garbage creation. So we're going to talk more about the creation side of this. I just realized how gross that is. Anyway, so talk format. Let's move forward. I have 150 slides in 35 minutes. Okay, let's do this. So there's not much code in this presentation. I won't have much code, and most of it is Ruby code that's in here. Some of it is C code. Well, actually, I don't have any C code. I've translated all of the C code into equivalent Ruby code so that we can kind of understand what's going on. There's also a lot of maths in here, and I want you to notice that I localized that, maths. I put L22N because I don't know how to spell localization, so I just guessed. Thanks. All right. So that's how. All right. So there's a lot of binary numbers. We're going to have binary numbers in this, which I actually learned binary numbers when I was in 2nd grade. My mom taught them to me because I wanted to have like secret codes so I could pass notes to friends in class. So I'm like, Mom, teach me how to do secret codes. And she's like, okay, I'll teach you how to do binary. And then so I wrote a bunch of binary. Of course, none of my friends cared to learn it, so one-way encryption. So we're going to review some algorithms as well, but I've done my best to make this talk accessible, so I'm going to break down what you should learn or what you should try to pay attention to depending on your level. I mean, if you don't know anything about Ruby's GC or about allocating objects, then I'd like you to pay attention to the high level of Ruby's memory format, the shape of it, and the relationships between each of the parts of Ruby's memory model. If you know about this stuff already, I want you to follow some of the C tricks that I'm going to show you in this presentation. If you know about those, then check out the compaction algorithms that we're going to talk about. Try to pay attention to what's good and bad about the particular algorithm that I'm going to present today. So we're going to do a deep dive into various aspects, but we'll come up for air pretty frequently. And in other words, I'm going to be repeating a lot of things over and over again just to make sure that we're all working together on this and we can all get something out of the presentation. So we're going to be focusing on object allocation at the beginning of this presentation. We'll look at object allocation first because I want to end up talking about object compaction, and we need something to compact, so we'll look at object creation before we do compaction. So I'm going to start out at a computer, and we're going to zoom into a Ruby process, go all the way down to bits, and we're going to look at each aspect of memory as we go down. So of course, my computer looks like this. It's exactly the same as this at home, including all the pixels. Very hard to type on. If we have a computer that's running our program, the computer has some amount of memory in it, just some block of memory. And inside that block of memory is the memory that our Ruby process takes. So our Ruby process takes some amount of that block. And we can actually divide that Ruby process's memory into a couple chunks. I'm going to ignore stack memory today, so those of you out there who know what I'm talking about, we're just ignoring that. We're only looking at heap memory today. We can split Ruby's heap into two parts, a managed part and then just some other heap part. So on the left side is where we keep Ruby objects, so those are things that we actually manage with the garbage collector, and on the right-hand side is just stuff. And what I mean by this stuff is, for example, if you create a string in your Ruby program, on the left-hand side we'll have the object that represents that string, and on the right-hand side is where we'll actually keep the bytes of those strings. So that junk on the right-hand side is stored in a separate location than the actual Ruby object itself, and the Ruby object itself points at that thing. So the managed side is managed memory, managed by the GC, and the other side is just stuff that exists. If the managed side goes away when we do a GC, that object is responsible for deleting its stuff, essentially. So the left-hand side is managed by the GC, and if we take that memory that's managed by the GC, we can actually split that up even further. The managed side is composed of many pages. So we have a page, and this entire block is actually composed of pages. So this whole block is just a bunch of things that we call pages. Now, a page has many slots in it, so we can take a page and further divide that down even more. Page has a slot. Actually, it's filled with slots like this. Slots can be in either of two states. The slots are either empty or they're not empty. So the word slot is essentially just a generic term for a free or a filled location. Now, slots can refer to each other, so if we have some code that looks like this, just some hash, the objects may refer to each other as something like this. So the hash will refer to each of its keys and values. So this hash object will point at those other slots. Slot is 40 bytes, so one Ruby object is 40 bytes. We'll fill that up with bytes there. I should have compacted it all together. But it's 40 bytes in size, and of course, one byte is 8 bits. And the 8 bits are just ones and zeros. We're going to be using the number 8 a lot. 8 is very important to us. 1 byte is 8 bits. And you may be asking yourself, why is 1 byte 8 bits? And I'm not going to say that the reason is aliens, but it is. So to recap, we have our memory, our full memory. We have Ruby memory. We can divide that down into a managed page and a just random data page. We can divide the managed page to multiple pages. Inside each page, we have slots, and then inside each slot, we have some bits, bytes and bits. So let's do a little recap on how memory is handled in C. Of course, in C, we actually have to manage our own memory, so we say, hey, operating system, give me some memory, and then when we're done with it, we have to release it. And of course, this is where a bunch of bugs come from, and why we enjoy GCs today is because they handle all that stuff for us. But in C, we actually have to do all that stuff ourselves. But when we allocate some memory, what is that thing that we get back from the operating system? We can actually think of that as just an array. It's just an array of data. You can think of it as just an array, and we can split up that array into multiple sizes, any size we want to, really. But for example, we'll split it up into bytes, so bite-size pieces. So for example, we may have memory layout like this, where we have different addresses, and those addresses are essentially just indexes into that array. So you can imagine if you have an array, the indexes are just addresses, and these addresses are unique. And I kind of like to think about this as, for example, a neighborhood. So if you want to go visit your friend, you need to have your friend's address. So if you look up you take their address and you look up their location, you can go see what data is at that address. But an interesting thing is you don't actually have to go to their house if you don't want to. If you get somebody's address, you don't need to go there. So indexes into this array are addresses. Addresses are unique. Visiting a house isn't required, so if you get somebody's address, you don't need to go there. This will become important in a minute here. But if you get someone's address, you don't have to go there. So let's take a look at objects without allocations. So you may or may not know this, but everything in Ruby is an object, but not all of them require allocations. And we're going to look at how that is accomplished with Ruby. We're Ruby programmers, all of us here, I hope. Although I heard that there are some Elixir programmers here. Most of us are Ruby programmers, I suppose. But MRI is written in C, and we can actually take advantage of this implementation detail to represent objects without doing any allocations. So Ruby objects need to move back and forth between the Ruby runtime and the C implementation of MRI. Now, we can do some tricks with this. So Ruby objects are about 40 bytes. Not about, they are exactly 40 bytes. And Ruby objects are aligned on 40 bytes. And what that means is that a Ruby object, when it's sitting in memory, the address of that Ruby object is divisible by 40. So we can knowing that fact, we can do some tricks with that. When we pass a Ruby object into C, we're not passing the actual object, we're passing the address of that object. So in C, we can say, hey, is this address divisible by 40? If so, we're going to go look up that object. If it's not divisible by 40, we can go do something else, okay? So if we take a look at addresses divisible by 40, these are just some numbers. Each of those numbers on the left-hand side is divisible by 40. On the right-hand side is the binary representation of that number, and you'll notice something in common with all of those binary numbers, and that's that the last 3 bits are always 0. So we can use those last 3 bits to give some meaning to that particular address. So as we pass a Ruby object into C, of course, if it's divisible by 40, we'll go look it up. If it's not divisible by 40, we can examine those last 3 bits and figure out something interesting to do with that. So for example, we'll say if the very last bit is a 1, then let's take the address and shift it right by 1. And we'll get an integer from that. Conversely, if we're taking something from C and passing it into Ruby, so for example, we have the number 13, we can shift that left 1 and then add a 1 to it and return that object to the Ruby runtime. And we're not actually accessing any memory at that point. So to give you a concrete example, we'll say here we have some C code, and this C code passes an object back to Ruby. We'll start out with the number 13. We want to pass the number 13 into the Ruby runtime. What we do is we shift that left 1, and then we set the very last bit to 1, and then return that. So in binary, that'll end up with the number 27, and in binary, it'll be 11011. Now, if we go in the opposite direction, we can take the number 13 and pass that into C, and I've kept the binary there on the right-hand side to have a key. If we pass that into C, what we can do is take that address, and we see, oh, it's not divisible by 40, let's do our special case, and in that case, we'll shift it right by 1, and now we're back to the original number 13. So in this way, we can take integers and pass them between Ruby and C and never have to do any allocations to represent that number. We can encode those integers and pass them between the two languages. So we can actually verify this in Ruby. If you take the number 13 and you call inspect on it, of course, it's just going to show you the number 13. But we can unbind the inspect method from kernel, then rebind that onto integer, and it'll show us the normal inspect object that you're typically used to. And you'll see that the address of that integer is OX1B, and if we print out OX1B, you'll see it's the number 27, and it's actually 11011. So we can verify that this is the behavior in MRI. Of course, this is probably not going to work on any other runtime. So knowing this stuff, we can actually figure out what the maximum integer is without allocations. So my machine here is a 64-bit machine. We need 1 bit to represent the sign because we can have positive and negative numbers. And we need another bit for this encoding bit that we're using. So we're down to 62 bits. So the maximum integer we can represent is 2 to the 62 minus 1. So if we print out that number, you'll see this large number, and if we bind that inspect onto the object, you'll see the object ID is that OX7 and then a whole bunch of Fs. So stuff to remember from this: Ruby object addresses are divisible by 40. We can use those remaining 3 bits on the end of that number to encode objects. We can have some sort of encoding to go with that number if it's not divisible by 40. This technique is called a tagged pointer. Now, the trick behind these tagged pointers is that it allows us to represent objects without requiring allocations. We can represent objects without interacting with the GC at all. And there's a bunch of other objects besides integers that don't require allocations. And if you go check out the object ID method in gc.c, you'll be able to see a table of all the objects that are represented using this trick, and also which objects those are. It's integers, floats, true, false, nil, and I think symbols. There might be something else, but go check out that table. So, all right, we haven't actually allocated anything yet. I told you we were going to talk about object allocations, and we haven't actually allocated anything, so let's do some real object allocations. So, as we said, slots live in pages. We have a page. The page has a bunch of slots. And these slots are in either 2 states. They're free or not. So it's a free space or an object. These free slots, they're kept in a list. So there's a list between all of these free objects. And the page, at the header of the page, we keep a pointer to the header of that free list. So as soon as an object is allocated, the way Ruby works is it says, okay, let's just take that very first address, the very first thing on the free slot, or free list. We'll use that as our object. see if I got my builds right. When we do object x equals object.new, that will allocate an object. The GC takes the head of the free list, and that's what's used as the slot for that object. Then it bumps that next pointer forward and continues on. So we repeat this process over and over. So we'll say y is a new object. When the allocator runs, we grab the first thing off the head of the free list and then continue forward. So we push this pointer forward on each allocation. Go, build. Yes, there we go. So this list of free spaces, this list of free slots is called a free list. This is our free list. It's just a list of free spaces to put objects. Bumping this pointer forward is called bump pointer allocation. But I don't know if you noticed this, but we're still not actually allocating any memory. This memory has already been allocated. We're actually just taking an existing location and writing an object into that particular place. So we haven't actually allocated any memory. The memory was already allocated. We're just taking that space and putting an object in there. We're writing to that location. In other words, we're just filling this free slot. So what happens if our page is full? Ruby will do a GC, and if there are any free spaces after the GC, it'll give you that slot. If there are no free spaces after running the GC, then Ruby will actually allocate a new page. So we'll get a new page. The new page will be filled with free slots. That'll become a free list, and we'll just do this process over again. And this is actually our very first call to Malloc. This is the first time that we actually asked the operating system for some memory. So everything we've seen before this already had memory allocated or didn't require any allocations at all. This is the very first time we've actually required memory from the operating system. So what size do we ask for? How much memory do we ask for? Well, one page is 16384 bytes. It's not actually that. It's 2 to the 14th, so that's 16384, but we actually subtract a small amount of memory from that. And the reason that we subtract this small amount of memory is because when you ask the operating system, like let's say you say malloc 10 bytes or whatever, the operating system doesn't allocate 10, it allocates 10 plus some amount for bookkeeping. So we have to take that bookkeeping into account because our goal is to allocate exactly 16 kibibytes. Sorry. I'll explain this in a minute. So one OS page is, oh God, I hate saying this. I want to be accurate, but the word is so terrible. One OS page is 4 kibibytes, and we want our Ruby page to be exactly 4 OS pages. So when we allocate that 16 2 to the 14th, we have to subtract some from that in order to make sure that it fits with 4 pages, including that header for malloc information. So let's talk about this confusing nomenclature here. We have 1 kilobyte is actually 1,000 bytes, and if you look at that in binary and compare that to 1 kibibyte, which is 1024 bytes, you'll see why this difference is important. These binary numbers are much more handy when they're divisible by 8 using this scheme. So the reason I'm bringing this up is because wording is actually important. If I were to tell you kilobytes and it was actually kibibytes, you're going to be getting more data. You could mess up your math. It could even go so far as to cost you money. So for example, if you went to the store and you're buying I typically go to the grocery store to buy hard drives. You're going to the grocery store, you need a new hard drive, you're looking at the package, and you think you're buying a one tibibyte. I think that's the right word. But it turns out it's only 1 terabyte. That's the difference between the two, so it's important to know this, to know the difference between these two words. Now, unfortunately, in real life, kilobytes means 1,000 and 1024 at the same time, which is extremely confusing, so check your math. Anyway, this is I think that this is part of me thinks that this is extremely confusing, but the other part of me that lives in a country that uses the imperial system thinks it's just fine. What? Pound, what even is a pound? Anyway, So this is our very first call. This is our very first call to the malloc function, and this is actually an aligned malloc. We're doing an aligned malloc. Now, what is aligned? What does that mean? Now, normally when you do a malloc and you ask the operating system for memory, it's just going to return this array of this neighborhood to you, this chunk of memory, and the address is just going to start wherever. The addresses are always unique, but the first address is just going to be some number. Now, one thing you can do is you can do an aligned malloc where you say, hey, operating system, give me some memory, but I want the first address to be divisible by some number. So for example, if we were doing an aligned malloc of 10, it means that the first address that comes back to us will be divisible by 10. So maybe it's 20, maybe it's 30. It could be any number as long as it's divisible by 10. So the addresses will be unique, but the very first address will always be divisible by that number. That is what an aligned malloc does. So in Ruby, what we do is we say, okay, we're going to do an aligned malloc. We want that alignment to be 2 to the 14th. And we want the size to be 2 to the 14th minus a little bit, as I said earlier. So the very first address is going to be divisible by 2 to the 14th, and the size will be 2 to the 14th. And that is an interesting technique because it means that no addresses inside that chunk will be divisible by 2 to the 14th except the first one, because it's smaller than the size. So a Ruby page will look something like this. The first address is divisible by 16384 right there, and because this page is smaller than 2 to the 14th, all of those numbers will not be divisible by 2 to the 14th except the first, and this is important a little bit later. So doing this technique ensures that Ruby pages align with operating system pages. So we make sure that the Ruby page aligns. The Ruby page is 16 kibibytes, and it aligns on the operating system's 4 kibibyte pages. And this is important. It means that we are all on the same page. Yes! Your pain energizes me. I feed on your pain. This is the only reason I tell puns, is because looking at people cringe gives me so much pleasure. Anyway, so this is important for a couple reasons. One is that we can determine page based on address. We know that a page is going to be divisible by some number, and we know that the pages are going to be aligned with operating system pages, so any copy on write optimizations will always take 1/4 of that page and copy it down. So we can do a similar trick with these pages that we were doing with the objects before. If we look at this, on the left-hand side is our decimal 16384. Each of those numbers are divisible by that number. And if we look at the binary representation, we'll notice that only the top bits change. The bottom 14 bits do not. They're always zeros. So those bottom 14 bits never change. What this means is we have sort of an address encoding where this top part of the address indicates the page that an object is on, and the bottom bits indicate the actual object inside of that page. We can even split this down even further, where those last 3 bits are our tagged pointer. Those last 3 bits are always going to be 0 if it's an actual Ruby object. If it's not a Ruby object, those 3 bits are going to have, one of them will have a 1 inside of it. So we have page alignment and object alignment. We align pages when we allocate them, and we align objects inside of those pages. So a weird thing about this is that page addresses are divisible by 16384, but you'll notice that object addresses are divisible by 40, and this number, 16384, is not divisible by 40. So what do we do? What we do is we actually have some wasted space in each page. When we allocate that page, we say, okay, well, this first address is divisible by 16384, and we need to figure out where inside that page we can place an object where it will be divisible by 40. So we have to calculate an offset. We calculate this offset. It's the head of the page plus some number, and that number makes that address divisible by 40. So it'll be, the very first object is going to be placed at 16384 plus n, where n is some number that makes it divisible by 40. And what this means, this is very weird and confusing when you're debugging memory issues, but because of this, this means that pages can actually hold a different number of objects. So if we take all these numbers and calculate them, what it means is that in MRI, one page will hold 407 objects or 408 objects. So this is kind of annoying when you're debugging memory, but this is why. So now you know why. We can actually take these addresses and find the page for an object. I did this in IRB. We can tell if we allocate those two objects and we look at their addresses and then we mask off those bottom 14 bits, we can find the pages where those two objects were allocated. And these two objects were allocated on the same page. This is useful for heap dumps, so if you're debugging memory issues in Ruby, you can use this function called objectspace.dumpAll, and that'll dump your entire memory as a JSON file. And if you look at the output of the JSON file, you'll see it has hashes in there like this, and that there's an address in there, and that address is the actual address in memory. And if we take that address and calculate the page, we can figure out we can group objects by page and figure out which objects are actually close to each other. And this is the code for doing that. So we can say, hey, let's figure out the page address for an object, and then we can group all of the objects by pages. So you can see which objects are close to each other. The other thing that you can do is figure out, since we know the size of the page, and we know that each object is on a 40-byte offset, we can figure out where holes in the page are as well. What this allows us to do is this allows us to figure out the page's fragmentation as well as locality. Where fragmentation is the amount of empty spaces in that page, and locality is how close together these objects are. So, in other words, emoji, I learned that yesterday. So, pages have slots. Slots contain objects. Locality is how close together those objects are. Fragmentation is how many holes there are in that page. So with that, let's move on to GC compaction since I have 8 minutes. Holy shoot. Oh, I shouldn't be wasting my time. Sorry. So what is compaction? Compaction is taking these objects and moving all of the actually allocated objects next to each other. So doing this, saying like, hey, let's take all these objects and move them next to each other, and the free spaces move them together. So why should we do this? Two reasons: reduce memory usage. This allows us to reduce memory usage based on copy on write optimizations, and it also allows us to free up pages, because the only time a page is ever actually freed is if it's empty. And we can use compaction to empty these pages and allow them to be reclaimed. It also allows for possible speed increases depending on the type of compaction algorithm we use. We can see speed increases because locality can be improved. So compaction actually has two steps, two high-level steps. These high-level steps are compression, taking those objects and moving them next to each other, and then reference updating. What reference updating is say we have a layout that looks like this. One object points to another one. If we compact these, move those objects together, all of a sudden now that object points at a free location. That reference went bad, so we have to update those references so that they're good again. Of course, this is bad because if we're pointing at some address and we go to that address, maybe the address is empty, or even worse, we have some scary clown at the address, and our program crashes. So the compaction that I've implemented is an algorithm called two-finger compaction, and what that is, it looks like this. Imagine that we have a heap that looks like this. Two-finger compaction is when we essentially have two fingers, or two pointers, one pointing to either side of this heap. One is called a free pointer, the other one is called a scan pointer. The free pointer moves right, looking for free slots. The scan pointer moves left, looking for filled slots. And when those two conditions meet, they swap them. So the free pointer in this case doesn't move, the scan pointer also doesn't move, so they just swap the two. And then we leave a forwarding address there. So we say, well, the object that used to be here, it is now located at address 1. Then we move forward. The free pointer moves forward to the next free location. The scan pointer moves backwards until it finds the first object, or the next object. Then it swaps the two. It adds a forwarding address, and then we keep doing this procedure until eventually we've compacted the entire heap. So we move forward to the free, this one moves back to the object, they swap the two, and now all of the objects are next to each other. So once the two pointers meet, then we know that this algorithm is complete. The next step is we have to actually update addresses. So if we have a heap layout that looks something like this, before compaction, when we actually compact, maybe it looks like this now. We have to update the references. So the way we do that is we move forward, looking for objects that have references. This is the first object with references, and it sees, oh, these ones, the new location is at 5 and 2, so I'm going to update this to point at 5 and 2. And then it just keeps going through the rest of the heap, updating those references. Then finally, it takes all those forward addresses and converts them into free slots, and then we're done. This is the compaction algorithm. So challenges with this are trying to figure out what things we can't move. So anything that depends on an address prevents that object from moving. So for example, an object ID, when you use object ID, that object ID depends on the location in memory. This is an example of preventing an object from moving, though we have a solution for this. Another example is hash keys. Hash keys depend on where the object is in memory to calculate their hash key. If we moved your object, and that object was used as a hash key, all of a sudden you wouldn't be able to look up that object. So we have to prevent hash keys from moving. The other thing we have to prevent from moving is object literals. So for example, if you have a string in your code, something that looks like this, we have to prevent that from moving because instruction sequences point at it. Holy shit, I only have... backspace, backspace, backspace. So instruction sequences point at these raw addresses, so we can't move those today. And these are some challenges that can be overcome, but I think the reason this technique hasn't been used so far is that the most difficult thing is, say we have some C memory pointing at a Ruby object. So for example, you have this Ruby code. It's accessing a SQLite database, and it's just iterating over the results. So the way this may work is that it takes this block, each takes the block, and it stores that block off into a location and says, SQLite, please execute the statement, and for each thing in the statement, I want you to call back out to the block. So we have to pass that block off somewhere else, and then some C code calls back into it. So we might have some diagram that looks similar to this. So we have an object that points at some C data. The C data points back at a Ruby object. These are so-called hidden objects because they're hidden from the Ruby interpreter. Now, it would be bad to move that block because now this C code has a bad reference and we would crash, right? Or even if the block got GC'd, say that block got GC'd, it would go away and then we would get a crash. So in order to prevent the block from going away, C extensions actually have to mark that, and the way they do it is by calling rbgcmark. So to fix this issue and find where these hidden references are, what I've done is I introduced, well, not introduced, these already existed, but I've split the marking functions into two. We have rbgcmark, which is a public function, and we have gcmark, which is a private function only used inside of Ruby. So the rbgcmark, if that marks an object, we know I can't move that. It's accessed by some C code that I can't touch. So then we can, once we use that, we can figure out how to update these references. So when we do this compaction, we actually take 4 passes on the heap. One is to mark the heap, to find those unmovable hidden objects. The next step is to compact the heap. The third step is to update all of the references. And finally, the fourth step is to set the forward slots to free. So we can take a look at some of this in action, some graphs of this. I have an example here of a Rails heap. This is the compaction code that I'm using. I just start the GC, dump the entire heap, compact. You'll see there's a new function there called gc.compact. Compact the heap, and then dump the heap again, so I can see the differences pre and post compaction. And this is what it looks like. Each of those bars, vertical bars, is a page, which we've talked about already. The red bar inside the page is slots that cannot be moved. The green is slots that can be moved, and you'll notice the top of that is jaggedy because each of those pages hold different numbers of objects. So this is before compaction, and this is what it looks like after compaction. You can see that we've moved all of those green objects together. So if we count the number of pages that had free slots on them before compaction, 528 out of the 552 pages had free slots, which means that that's the number of pages that could possibly see copy on write faults. After we do compaction, we have 167, only 167 pages have free slots on them, so those are the only ones vulnerable to copy on write issues. So this is good, but it's not great, because not all, we ended up with the same number of pages. We would have expected these pages to go down. We expected the number of used pages to drop. Unfortunately, it didn't. Ideally, some of these red bits would go away, and we would remove some of the pages. But the good news is that we know how to do this. It's merely just figuring out how to update the references for those different types of objects. So the next step that I'm working on with this are essentially to fix object ID. Today, if you use this code, I've got it posted on GitHub. If you do use this code, object ID is based on memory address. If you compact the heap, your object ID will change, and clearly people will not like that. You can calculate the object ID, or the address of the object, by shifting it left one. So the idea is we're going to keep a table. This table will keep track of objects that you've called object ID on, and then update them correctly if you compact the heap. The next step after that is I'm in the middle of writing this code. The next step is we're going to be using this in production. In production, the way we want to use this is boot our Rails application, compact the heap, and then fork all of our child processes in order to reduce copy on write fragmentation. And then finally, we'll push this upstream. Future optimizations, fixed string and symbol hash keys, allow those to move, allow literal references to move as well. So I want to wrap this up now, since I think I am over time a couple minutes. Ruby's heap has many pages. One page has many slots. A slot can be empty or full. You can debug your heap using objectspace.dumpAll, and GC compaction brings all of this closer together. So, in other words, all this technology, the mathematics, the alignments, the algorithms, the bits, the bytes, all this hard work and computer sciencey stuff is all done just so that all of us here today can build graphs of our cat's poop. I am trying to waste as much technology as possible. I will leave you with that. Thank you.